Hey, physics kids. We're going to be talking about magnetism today, and let's look at some basic properties of magnets. Well, first of all, each magnet has a north and south pole. Always has a north and south pole. What we know, like poles repel and unlike poles attract. Okay? So each magnet, the like poles will repel each other, and unlike poles will attract each other. But I bet you knew that. A compass is a suspended magnet, right? The north end points north. Okay, very simple. The north end of a compass points to the north. Do we have any trouble with that? Well, why should we? The north end points, the north end doesn't point north. The north end, that's the south end of a magnet. The north end points to the south end. So how do we deal with that? Don't we have a little bit of trouble from our Boy Scout training? Because what I learned was that the north end of a magnet is supposed to point to the North Pole. Well, we have to deal with this. So do we call this then the south end of a magnet? That's going to get very confusing. We're going to start losing Boy Scouts in the woods all over the place. So instead, if this is the Earth, this is the North Pole of the Earth, what we say very quietly, and we never really talk about it again, is that the south end of the Earth's magnetic pole is there. That's really the south end of the Earth's magnetic pole. Now, don't worry about that. Don't ever think about it again unless someone says to you, hey, how is it that the north end of a compass points north? That's the solution. So the north end of the Earth's magnetic field is on the other side of the planet. Okay. Some basic magnetic substances are cobalt, nickel, iron. Now there's a number of others. But why are they magnetic and why aren't other substances magnetic? To understand all this, please look up and watch the Veritasium episode on magnets. It will blow your mind. It is very, very useful to watch that and understand it. It will help you tremendously towards understanding magnets. So a permanent magnet, like something like this, they keep their magnetic field for a long time. And an induced magnet is when something like a permanent magnet touches a magnetic substance. That substance then becomes magnetized, but it'll lose that property upon separation. For example, these are just some paper clips. They are clearly not magnetic. But if I touch the paper clips to this magnet, you will see they become magnetic. Now this one has become magnetized, and it can pull another one. But each one, the farther it gets from it, has less and less magnetism. Can it pull that train? No, that just barely can pull it. How about that one? Can that do it? Looks like we've run out of magnetism by the time we get there. Okay? But if I detach that, these will be magnets for a little while, but they will quickly lose that property. Look, this is still hanging on. But if I come back in a little bit, these will not stay magnets for much longer. All right, so to induce magnetism, you have a strong magnet touch a magnetic substance, and briefly it will become magnetized. But after a little bit, usually very quickly, it will cease to be a magnetic substance. If you watch that video, or when you watch that video, you will understand a lot about magnetism, because we will then be talking about domains. So any magnetic substance is made of domains. The domains are tiny areas. They're about 1 millimeter in size, where all the atoms are basically aligned in the same direction. To make the magnetic substance a magnet, the domains need to align with each other. So take a look at this. This would be a magnetic substance, but the domains are not aligned. All these little, about sand-sized areas, they're all randomly aligned. So overall, it's not a magnet. If I could get the domains to all line up, now I have a magnet. And that basically explains a lot about how magnets work. So to understand them, you really need to understand about domain theory. Well, let's talk about magnetic fields. Lines of magnetic force can be drawn from one pole to another. These imaginary lines can help predict what will occur as two magnets get close. The more lines, the greater the magnetic force. So the number of magnetic field lines is equal to something we call magnetic flux. Well, around any magnet, the lines are just strong. They have magnetic strength. How do we determine which way they run? Unlike gravity, you can really name them running both ways, sort of like an electric field. Remember, for an electric field, we used a positive test charge. That's how we define how electric field's direction goes. Well, what are we going to use to figure out magnetic fields, right? Well, we already have a device. We have a compass. So whichever way the compass needle will point, that would be the north end, typically the red part of a compass, that is the direction of the magnetic field. So, very simple convention, we use a compass. Don't get that confused with a positive test charge. Well, magnetic flux then. The lines form closed loops and never cross. Closed loops and never cross. So examples, the Earth's magnetic field is about 0.5 Gauss. So these are new units, and we're not really going to use them much more in this class. The typical sun field would be about twice that, about 1 Gauss. A fridge magnet, your typical fridge magnet, not very strong magnet, would be about 100 Gauss. A sunspot would be about 4,000 Gauss. Sunspots are purely magnetic. An MRI magnet would be about 20,000 Gauss, or about 2 Teslas. All right, 1 Gauss equals 1 times 10 to the minus 4th Teslas. All right, that's how those units work out. All right. Another idea here is permeability. Now, permeability is just, it's the property of a material that allows it to have a greater flux density. Sorry, permeability. Right? Property of a material that allows it to have a greater flux density than a vacuum would have. So here would be a north and south magnet with magnetic field lines drawn. This would be a permeable substance, and it kind of, you see, pulls the magnetic field lines into it. So that would be a permeable substance. All right, well, that's the idea of magnetism. Let's play with this a little bit. So I have, how about we start with this? I have a magnet here, and let's see what it would look like if I put iron filings gently upon it. You can see, okay, these outline the magnetic field lines. Now, you might have the sense that, well, there are the magnetic field lines, but again, this has to do with domains. So the magnetic filings that I have put upon it, they all align immediately, and so their domains line up, and so they attract the other magnetic filings. But it would be wrong to say there's no magnetic field in between these lines. So that's where you get the idea the lines are imaginary. And you can see the lines are connecting the north and south. Now this is just a single magnet. Let's see how it works. With two magnets. All right, so when we have two magnets, I want to show you what an attractive interaction looks like. This is north-south. Notice they attract. So if I pull them far enough away so they don't pull themselves together, and sprinkle filings on that. First of all, the magnets themselves are immediately outlined. And you can see there's a very strong attraction. The lines are very strong between them, and it attracts the iron filings right away in between them. If I try this again and pull them a little farther apart, you get a little bit of a different view. And you can see the magnetic field lines are very strong pulling between them. Nice. All right, what would it look like, however, if I have a south-south interaction? This would, of course, be exactly the same as a north-north interaction. I'll get these guys kind of close so you can see what would happen here. And you can see there's really no lines here. The lines immediately come up and spread out from there. All right? So let's just show you that a north-north interaction would give you the same results. I'll put these a little further apart. And you get the sense, again, the lines come out and push each other apart and spread apart like that. So that would be the magnetic interaction there. One more that would be interesting is the horseshoe magnet. So what's going to happen on the horseshoe magnet? And you can kind of see just what you'd expect. Between the two opposite poles of the horseshoe magnet, you have the lines clustering up there and connecting. So that's some basic ideas of magnetism and how these things work. The next thing we're going to be talking about is how electricity and magnetism work together. Thanks so much for watching. See you next time.